This is the Busch Microtronic 2090 computer system. It was released in 1981 in West Germany and was a beginner's computer system designed to allow people to understand and learn assembly language and machine language programming. Underneath the smoked cover here, we can see a computer system board on the right-hand side and the separate and optional cassette interface adapter board that allows you to save programs to audio cassette tape. If you'd like to learn more about the Microtronic system, I encourage you to watch the videos of Wessel. His videos are available on YouTube, and he grew up in Germany but has done some excellent English language videos on the Microtronic. He's also created a number of recreation devices which simulate the Microtronic and allow you to program it on modern hardware. In this video, I want to tell you a little bit about the reverse engineering that Michael and I have been doing to try and create a more faithful recreation of the Microtronic. In particular, we have downloaded the ROM, or read-only memory, and the firmware that lives inside the chip here, the TMS1600. This work was carried out with the collaboration of another colleague of ours, Wessel. I've entered a simple program into the Microtronic here, one that simply adds a number to the register and outputs it on the display here and on the outputs here. And if I just press the run key, as I've already entered that, you can see it going through and slowly counting through. Now I'm going to use this program to uncover and discover another feature of the TMS1600 CPU at the core of this device. In addition to allowing the customer, in this case the Busch company, to provide ROM or firmware or an operating system for the chip itself, they also allowed the customer to define the mappings from the output pins on the chip itself and how they connect to things like the display, and in the Microtronic's case, the SRAM, which is seated in this white socket here. While it's been possible for us to directly download the code from the ROM on the chip and reverse engineer this to a certain extent, ensuring we have the correct mapping for the OPLA, or the output programmable logic array, that specifies the connection between those pins and the display and RAM is essential to fully recreating the device. This is the schematic diagram for the Microtronic. It provides a logical overview of how the independent components are connected together to build the system. If we look for the O outputs, we can see them in two different locations. First, here along the top, we see O0 through to O7. These are connected via these resistors to the display unit, the TIL393-6. This is the 7-segment bubble display we see at the bottom of the unit. If we look closely, however, we can see O outputs in a different location, just here. These four outputs, O0 through to O3, connect to the RAM unit. These provide the lower 4 bits of the address to the RAM unit. The higher bits are specified by the R outputs here. While the R outputs are individually addressable, as we've already mentioned, the O outputs are controlled by something called the OPLA, or Output Programmable Logic Array. How this works is comprehensively described in the TMS1000 family microcomputers databook, and a series of programming manuals that goes along with it. Fortunately, we don't have to know exactly how all of that works or read all of that documentation to understand the OPLA, and we can just look at this diagram here from page 10 of the databook. Here we can see a default OPLA for a TMS1000 series computer. These microprocessors are all 4-bit in nature, and so the A register here provides only 4 bits of data, A1, A2, A4 and A8. We get an additional piece of data from the SL register, or the status latch. This allows us to configure 2 different output configurations depending on whether or not the status latch is set. The recommended or default configuration provides a hexadecimal display when connected to a 7-segment display as demonstrated here. And indeed, the Microtronic does indeed provide a 7-segment display and represent the digits from 0 through to F. If we look closely at the Microtronic schematic, however, we can see that instead of connecting to the O1 output pin here to the first segment of the display, we actually connect the O0 output to the first segment, or the A segment of the display. This has the effect of moving this part of the OPLA down by 1 block. This OPLA also has 20 different configurations available along the bottom here. We call these 20 different terms. However, this is only true for the lower series of the TMS1000 series microcomputers. The TMS1600, being a more advanced CPU, provides up to 32 configuration options, and the Microtronic does indeed take advantage of those. In addition to the hexadecimal display, 0 through to F, it also uses this additional area in the full 16-bit wide space to provide outputs to address the RAM, as we can see here. Now, it would be unsurprising to find that the O outputs are configured from 0 to map to a 0 binary output on these addresses here, and for 1 to a 1 output, and so forth. But what we don't know is what's happening to the additional pins 04 to 07 when it's accessing the SRAM. Are these left floating? Are they set high? Are they set low? Or so forth. To figure out, we can use a logic analyzer. So I've gone ahead and bought one from AliExpress, and this is the logic analyzer I received. It's a cheap 8-bit logic analyzer, and it cost me approximately £2 to £4. It comes with the required USB cable and some colourful ribbon cable as well. However, it doesn't come with any pros on the end. If you're going to connect this to a breadboard or some pin headers, this is perfectly adequate, as you can plug them directly into your breadboard or into the Arduino, for example. However, as we want to connect this to some chips in this video, I've gone ahead and purchased some little mini grabber probes as well, and these cost me an additional £4 or £5. To access the entire RAM, we need to exercise the entire RAM address space. And so I'm going to show you a little more about how that program, which we just saw running, actually works. This is the complete program counter with binary output. And the first thing it does is it clears the built-in registers in the TMS1600 and then chooses to display the complete set of registers from 0 to 5, so 6 registers on the display. It then goes through and adds 1 to the first register, register 0, and provides some code to allow overflows to happen, so that when we get to F, that loops back around to 0, but it also increments the digit next door, and that happens all the way through to here. It then additionally sets the output register onto the output display so that we can see the blinking lights as we saw on the binary outputs. And then, just to make sure that we use up the full 16 different addresses on that lower 4 bits of the address space from 0 through to F, I've gone ahead and I've added some no operations here, just by filling this with zeros. In truth, this actually moves register 0 to register 0, which is essentially a 0 operation. Finally, once it's done all of these no operations, it gets to the 16th address, OF, and it uses this go to go back to position 02 here, which again adds 1 to the 0th register and increments through, and eventually we'll see this overflow. And so this loops through continuously, as we just saw in the preceding section. So I've gone ahead and connected my logic analyzer to the TMS1600 at the core of the Microtronic. I've connected probes D0 to D6 to pins 0 to 06 on the TMS1600. In the Microtronic, these pins are used to drive the individual segments of the 7-segment display. While the Microtronic does control the decimal place on that display using the 07 pin, I've elected not to connect any logic analyzer probe to that pin in this instance. Our cheap logic analyzer here only has 8 channels, and I'm already using 7 to monitor those 7 segments of that 7-segment display. Instead, I've reserved our final channel, D7, to connect to the R11 pin here on the other side of the TMS1600. In the Microtronic, this pin is used to indicate whether or not the CPU is accessing the display or the RAM. The Microtronic uses the lower 4 bits of the O outputs to address the RAM, addressing the lower 4 bits of the SRAM chip here in the white socket. I've also gone ahead and connected the ground wire to one of the emitters of these transistors here, which represents the ground reference for the logic analyzer. This allows us to detect whether or not a signal is high or low with reference to that ground point. There is one final wire on this logic analyzer, this white wire here, and that's used to connect to the logic analyzer's internal CPU and indicate its clock. Now, in almost all circumstances, that's not particularly useful, and so this wire is typically left disconnected, as you can see here. With all that set up, we are ready to go ahead and capture some data, and I'm using the Pulse View program here, as you can see on this little mini monitor. I've already gone ahead and configured the labels here so that the wires colours here are matching with the labels down the left-hand side. By default, for this logic analyzer, PulseView wants to collect 1 million samples at 20 kilohertz, but I'm actually going to up that rate to 500 kilohertz, which is the nominal CPU speed of the Microtronic. Now, usually you want to collect data at a higher rate than the CPU speed, but the Microtronic CPU only actually executes one instruction every 6 clock cycles, and so this is more than fast enough to collect data from this particular CPU. With all that set up, we can go ahead and collect some data, and we do so by clicking the Run button right here. Now this collects 2 seconds of data, 500 kilohertz, 1 million samples, and we can see that there's definitely data being recorded. This is because, of course, the TMS1600 is running. It's currently operating the display, updating that display, and it's also looking for keyboard inputs on the keyboard. We can zoom right in here, but that's not particularly meaningful to us. But fortunately, PulseView has some built-in decoders. So I'm going to zoom right out here, and we can access those decoders by clicking this button here. One of the available decoders, fortunately, is a 7-segment display decoder. So we can access that by double-clicking on that here, and it adds a 7-segment display decoder to the left-hand side. Now I'm going to go ahead and close this side panel due to space reasons. And I'm going to click here on this decoder to configure it. Now, fortunately, all our pins are in the same order as required here, so we can just go ahead and put all of our pins connected in sequence, so D0 to D6. And as I connect that last one, you'll see the green bar in the background has appeared, showing that the decoding has happened. Now, we aren't using a decimal place, which is why there's a dash in this line here, and we are indeed using common cathode, so everything else is set correctly. Now we can click off that configuration panel and we can see that there is indeed that decoded digits label here. And we can actually zoom right in and we can see what is actually being decoded. So we keep zooming in. And if we zoom in far enough, we can see we actually have what's being displayed on the display. We have 00, a blank, and then F08. And if we look here on this display, we can indeed see 00, a blank, and F08, although I recognise that some of those digits are obscured by the wires here for you. One thing you'll notice though is that the D7 wire here, or the D7 line, is always low. And in fact, if we zoom right out again by clicking this button, we can see that it's always low. Now the D7 line, as I mentioned, is used to indicate whether or not we're accessing the display or the RAM. And D7 is low when we're accessing the display. To actually get it to access the RAM, we need to run our program and then it will load all of the bytes or words of data out of the RAM in sequence as necessary. So what we want to do is we want to start running our program and we want to capture some data while that's happening. But what we can do here is we can use a little trick in the logic analyzer to capture data only when that signal finally goes high to indicate the program is running. And we do that using a trigger point. And to configure that, we simply click on the D7 label here and we specify the trigger type, and we want the trigger to happen when that signal goes high. This is indicated by this icon over on the right-hand side. Now, it's also useful sometimes to capture data before the trigger point, and so we're going to go ahead and do that as well by clicking this configuration button here, and we can go ahead and collect, say, 10% of our total data capture before the trigger point. Now, I'm going to go ahead and make sure the Microtronic is set up correctly by making sure the Halt button is pressed and press Next and 00, and this makes sure we're at the beginning of the program and we've set the program counter. And then back in PulseView here, we can go ahead and press the Run button, and this will arm the logic analyzer, but we won't get any data collected just yet. Data collection will only start when that D7 line goes high, which will happen when it loads the next byte of the program from the SRAM. So I'm going to go ahead and press the Run button now. And as you can see, data capture began to start, and we now have captured our 2 seconds of data. We can still zoom in and see what was on the display. And we can do so by just scrolling to the left here and seeing what was on the display at the trigger point, which is indicated by this line here. And this is when the trigger first went high, and we can see on the display, interestingly, we had 01 F08, which is interesting, but then the display it updated there, and we got the complete display of zeros. And if we scroll a little further across, we can see the display continues to be zeros until it switches to 1. Now, why does it switch to 1? Well, of course, because one of those instructions tells the computer to increment that first register. Now, where are we in that instruction sequence? We can find out by adding another decoder. So now we have all of these data lines, and we know that some of them are actually being used to access RAM, and some of these RAM accesses will be happening. And again, if we zoom out, we can see where these RAM accesses are happening. So we can go to the decoder panel again, and we can find another decoder that might be helpful. And in this case, we just want a simple parallel decoder because we want to decode bytes in parallel. And so I can search for a parallel decoder here. And I can just, again, double click that to bring the parallel decoder into view. And again, we can close the side panel. Now, we do need to configure the parallel decoder. First up, most of these signals are already correctly connected because, again, we are using D0 to D6. But we don't have a 7th data line, so we should probably turn that one off. What we do have, though, is we have a clock signal, essentially, for our purposes, on that data line. And so we can say that the clock signal is on D7. Now, if we leave it configured as so and we zoom out, we'll see that the RAM accesses always appear to be 0, and that isn't actually quite right. Now, this is due to the way the Microtronic actually accesses RAM, and the address is actually configured correctly at the falling edge, and it's not configured correctly when it first indicates it's going to access RAM. And it's just a sequencing order about how it configures those address lines. And so we can go into the parallel decoder here, and we can go and scroll down, and we can say we want to sample on the falling edge instead. And now we can see we can get all of our address accesses. You'll notice that we start at 1, and that's because when we set the program counter, it immediately loads the requested byte into the TMS1600's internal RAM, and so it doesn't need to load that again. It's only going to load from that additional point forward. But if we can go ahead and zoom in here, we can now see the display is all zeros until we get into that second address. We can see here that second word of the program, which is the one that actually increments that register. And so now we see 1 on the display. And if we zoom out again, just so we can see a bit more of what's going on, we can see the memory access does happen in sequence as we would expect all the way along. And when we get to F, we jump back to O2, right? Because that's what our program does. It jumps back to position 2. And if we zoom in here, we can see the display is 1 until it gets updated to show 2. So using our logic analyzer here, we've managed to understand the mapping to the display, which was essentially fairly obvious based on the fact that we can actually see it physically on the display. But we've now also managed to verify the memory access as well. Now, one important factor about the OPLA is that while we could already infer the exact positioning of the OPLA for the visible aspects, we can't do so for the non-visible aspects. But fortunately, now we do indeed know that our addresses do happen in sequence, maybe unsurprisingly. But we also know that the additional address lines are also set to 0 during that period. The decoder here is indicating that 0 is indeed the value that is in the higher nibble of that address from the O pins. Now, while they don't actually directly address the RAM, it's nice to know that those signals are indeed set low. And so in the OPLA, we would expect those not to be connected. Okay, I hope you found this an interesting video to talk about how the Microtronic works and how to use a simple logic analyzer to reverse engineer some internals of a proprietary chip.